Welcome back, and we're going to look at some further examples with trig derivatives. And so a classic example with trig, well, with a function that uses trig functions in general is some sort of band or spring, or pendulum actually too, anything that uses harmonic motion. And so here we have a particular band, and then a mass on the end of the band, and then you pull it downward, release it, and then it vibrates up and down, and then we assume ideal conditions so that it just continues forever and ever. Okay, and so here you're given other information, but what we want to do is we want to find the velocity and the acceleration. You might remember, maybe not, that if we have a function s of t that is position, then s prime is the velocity. So v of t, this is velocity, and its second derivative is acceleration. So then if I'm looking for velocity and acceleration here, all I have to do is differentiate them. So s prime is equal to negative 2 sine t plus 3 cosine t. And then that's velocity, and then the acceleration is minus 2 cosine t minus 3 sine t. Okay, and then if I graph them on a graphing utility, I have done this in Desmos. So here is the original function in red. In blue, which I just enabled, is the velocity function. And lastly, in green is the acceleration function. Kind of interesting. Alright, and so from here we have some questions. When does the mass pass through the equilibrium position for the first time? So equilibrium position, I'm just going to hide these last two. That has to do with the position function and when it hits. So 0 would be the first instance where it, or when s of t is 0, that would mean it's at equilibrium position, and it looks, at least graphically, at about 2.554 seconds, I believe is our unit. Yep, seconds. Okay, so we can answer that. And then, but that's also rounded, so we should maybe find that algebraically. Okay, we'll get there in a minute. We'll maybe answer these graphically first. How far from equilibrium position does it travel? So in essence, what's the amplitude? And that we could just look at a maximum and say maximum is about 3.6 centimeters. That's our unit here. And then lastly, when is speed the greatest? And so that is looking at really on the velocity function, where are these points that cause maxima? Okay, so we'll get all that here in a moment. Okay, now graphically we can get estimates of the answer, but it would be nice to get exact answers. So for some of this, when does the mass pass through the equilibrium position for the first time, you would set s of t equal to 0 and solve. So that is equal to 2 cosine t plus 3 sine t. And so then manipulating this around, you get tangent of t is equal to negative 2/3. And then so then for t you can find arctangent of negative 2/3. Okay, and then also remember that you can add pi k to it for the periodic component. How far from equilibrium does it travel? So that for that you could look at, so you're effectively wanting to find the maximums or the minimums of the function, and I'm going to tell you that if you look at the derivative and set that equal to 0, that's going to give you the times that the times that correspond to those maximum and minimum values for S, and then you can plug those values in to get, or substitute those values in to find your maximum displacement. And then when is speed the greatest? Again, you're looking at when V prime, you're looking for the maximums of V prime, and if you set that equal to 0, you can find those times. You might have to confirm graphically. I'm not going to do that just for time purposes here, but we have the general idea. Next, very interesting example. So I'll give you a moment to pause the video and read it. So we want to look at this limit, and it would be helpful if we can figure out formulas for A of theta and then B of theta. I'm going to probably do A of theta and then I'll do B of theta down below. Okay, if I think about A of theta, well, that's a semicircle, right? So that is going to have the equation pi r squared over 2, okay? And I need to figure out an expression that relates r and theta. And to do that, I can say that I might have to do a little bit of dissection here. Okay, if I can imagine, so split this. This is isosceles, so I can say that this is theta over 2. And this then would be r. So if and I know what 10 is, so I could say that sine of theta over 2 is equal to r over 10. So effectively, 10 sine of theta over 2 is equal to r. Okay, so then I can just say that this is pi, and then 10 sine theta over 2 squared all over 2. And simplifying, I get 50 pi sine squared theta over 2. For B of theta, okay, formula for triangle, right? Well, it's going to be 1/2 base times height. And so the base is length 2r, and the height I can go ahead and find, or actually remember that there's the formula for area 1/2 a times b, where there are adjacent sides, times sine of the included angle. So that actually makes my life a little easier, as I can say this is 1/2 10 times 10 times sine of theta. Okay, so then from here, and actually that simplifies to 50 sine theta. Okay, so then this limit, as we approach 0 from the positive side, would just be 50 pi sine theta over 2 over 50 sine theta. And certainly from here the 50s can reduce, but then thereafter the pi would come out front as well. From here on out, though, it gets a little algebraically intense. So I'd have pi limit as theta goes 0 from the right, and then sine of theta over 2. And what I'm going to do is insert a theta over 2 here, and then, actually I'm just going to insert theta. Or actually theta over 2 and then times theta over 2. And then similarly, I'm going to, this is also multiplied together, I'm going to do sine of theta here, and then theta here, theta here. And what this is going to allow me to do is these, I've kind of set it up so that this and this, I could use that limit property to recognize that it's just going to be 1. This one you'd have to do a little bit more work, do the reciprocal, blah, blah, blah. It ends up being 1 as well. But then for this part, the thetas would end up canceling, and you'd have another 1/2 out front, so it would look like pi over 2 limit as theta approaches 0 from the right side of sine of theta over 2 over theta over 2 times limit, and then if you were to rewrite this just a little differently, this could be envisioned as 1 over sine of theta over theta. Both of these are 1, so you end up with pi over 2 times 1, or pi over 2, and you'd be done. So you found your limit of those two areas. Kind of fun. All right, so be careful with the algebra, and also have fun.